first, do you guys all remember, this is a while ago, it's just like close to 20 years ago now, which is unfortunate. But do you remember, have you ever heard the Kanye West song called Through the Fire?
Mm-hmm.
Yeah, it's like the first song that made him famous. Talks about being in his car accident, and he actually rapped it with his jaw wired shut because he had like a broken face. So anyways, the hook on that, Through the Fire, that was from a song written by Shaka Khan. Shaka Khan wrote the original Through the Fire. To the limit, to the wall.
Oh yeah, I know it now.
Okay? Okay, so that's that. And those are the songs for this morning. Second thing is, we're not even close to being into the week 2 material, but we'll get there. Number 3 is come to lab tomorrow at your designated or newly designated lab times, and wear clothes that you can be physically active in. You don't have to whatever. It's not going to be super strenuous, but you don't want to have dress shoes on. Roger that? All right, it's on record. Okay. So, the last place we left off on Friday, we were talking about how to, we were talking about a lot of random stuff, but one of the things that we were talking about that wasn't random was how to calculate work and the importance of calculating work and the fact that you can use work calculations and work measurements in order to look at physiologic responses and determine and gauge where an individual is in terms of their fitness, typically amongst their peers or a certain age group or those types of things. Did any of you take one of those introductory health classes where you do like a 12-mile run or a 1-mile run, and then you take your time and you look at a chart and it tells you what your VO2 is? Okay. So that is kind of a form of ergometry, not really, but you are like setting a specific physiologic task. You're completing it with the assumption that you've completed it at max effort, and then you're looking at that and gauging based off of regression analysis. That should ring a bell from EXS 312. You can figure out kind of where you are amongst people that are your gender, size, weight, age, these types of things. You understand? All right. So one of the things we talked about was the bench step and how effective and how easy it is, because you can, hey, Trent, what are you working on?
Notes for this.
Appreciate that. I'm very insecure. I want to make sure students are paying attention. No, you don't have to prove it.
No,
you don't have to prove
I want you to know.
I like it though. I like that though. Thank you. So I wasn't trying to put you on the spot.
But you did.
I was curious.
And now it backfired.
Was that a spot?
It was.
It didn't. I wasn't trying to prove a point.
Okay, just making sure.
Really wasn't. Okay, so the bench step is really good because you have a vertical distance on the bench and you know how many steps you take, and you can figure out your vertical distance, you have your force. You're really, in many ways, generating that amount of force because you're not generating a lot of horizontal force because you're just going up and down on the step. So it's a really good sort of measure of work. We can also use a cycle ergometer to measure work. We can also use a treadmill, but we're making the assumption that we're losing the horizontal component of that work generated, and we put the treadmill on a rise, and then what we do is we can measure vertical distance covered based on the total distance and the percent grade of that rise. All right? So I really want you to be familiar with those types of things because those are the things you're going to manipulate tomorrow in your lab. All right? So we'll talk about it a little bit more at that point tomorrow. Okay, so there's an example with the treadmill. I'm not really going to go through it, but we have a 60 kilogram, well, I'm going to go through it quickly, I should say. So you calculate Newton. That's the force based on the acceleration of gravity and the mass. You have the speed, you have the time, you have the grade, and from that you can figure out vertical distance covered. which turns out to be 150 meters. And now you can get force times distance, which is work, based off of vertical distance covered. Right? So you have access to these slides, so there's no need for you to like write down every single one of these numbers. Okay, so the next way that we can calculate work, so one of the ways that we've calculated work then is through joules or kilojoules based on force times distance, right? Another way that we calculate physiologic work or energy is through calorimetry. So this will be a theme of one of our, probably either our second lab or our third lab. Calorimetry is just what it sounds like. It's the measurement of the number of calories that a biological system consumes doing something or doing nothing, right? So even when we're just sitting here and it seems like we're doing nothing, biologically, physiologically, we're still doing a lot, right? We're breathing, our heart is beating, our liver's functioning, our gastrointestinal system is functioning, our skeletal muscles are turning over, or our bone is turning over. There's a lot going on, right? Our brains are thinking, hopefully. They're consuming calories in order to generate the neural impulses that are required for thought and memory and these types of things, right? So calorimetry is this measure of energy through measuring the production of heat by biological systems doing different types of activities. Okay, so we commonly measure this in calories, as it says here. It's important to understand, so the definition of a calorie is the amount of energy, the amount of heat it takes to raise 1 cubic centimeter of water by, or 1 milliliter of water by 1 degree Celsius. Okay, so that's how we've defined it. Now, that's a pretty small amount of heat, and we quickly get in, just like kilojoules, we quickly get into the thousands when it comes to talking about calories. So when we talk about calories, say, in the context of food consumption, we're actually talking about kilocalories there, all right? And we just call them calories because you just assume that if you're talking about food and you're talking about human biological systems, you're talking about kilocalories, okay? So 1 kilocalorie is 1,000 calories, obviously. The other thing that's important to understand is that calories have an equivalent in joules. And so like we talked about with European food labels, the energy from food is not expressed in calories, it's expressed in kilojoules. So if you knew how much food was in kilojoules and you knew how much work you were completing, you could match those things. Same thing with calories. Like we know how many calories are equivalent to joules or kilojoules. And so it gives us the ability to estimate the amount of calories that a certain amount of work completes. Does that make sense? So if you do a bench step test, we're going to calculate what? Work. Work is force times distance. Force times distance is newtons of force times distance in meters. Newton meters equals joules, right? So we get joules and kilojoules. If we have joules and kilojoules, we can convert that into calories and figure out how many calories it would take to generate that work or meet that work demand. Does that make sense? So all this stuff is just, and it's all just basic algebra. It's all just balancing equations. You have some knowns on one side, you have some unknowns on the other side, or you have some, you have things in one type of unit or express, and then we want to convert them into another, right? So it's just, see, can't you see up here on the blank board that I'm pointing to? Okay. All right, so why is this important? Well, we talk about calories a lot. We say that, oh, how many calories do you burn in a day? What's your basal metabolic rate? Everyone knows or has a general idea of this term called metabolism, right? So metabolism is, people when they talk about metabolism, they're typically referring to their, what's called their resting metabolic rate, or their RMR. And this is the number of calories that an individual would burn if they were to lay in bed awake all day for 24 hours. That's your resting metabolic rate. Right? The number of calories that's required to sustain your living and bodily processes without generating any voluntary work. That's your resting metabolic rate, right? Your daily metabolic rate then also includes everything that requires energy throughout the day. So you have your resting metabolic rate plus walking to class and exercising and recovering from exercise, and even digesting food requires energy. So one of the things, there's a concept called the thermic effect of food, or TEF, which it requires calories to process the foods that we consume. Right now, it's a small part of our daily metabolic rate, but still, daily metabolic rate are all those things that add up into total number of calories that you burn in a given day. And there's a lot of attempts to try and like capture this or measure it or estimate it, but those are just guesses, right? They're based off regression analysis that take what types of characteristics into effect. Those of you from EXS 312 as well as HWS 325 should know this. What types of things go into determining the amount of calories burned?
Age.
Yeah, height, age,
Gender.
weight. Surface area actually is a really important one. So as our like per per square centimeter or per cubed centimeter, as an organism gets bigger, the metabolism slows down. So for example, if you just extrapolated the metabolism of a field mouse up to an elephant and you just kept it linear, then the surface of the elephant's skin would be boiling. That obviously doesn't happen, so there's different, as larger animals burn more total calories, but they have slower metabolic rates per cubic centimeter of surface area, or per square meter of surface area.
But overall, do they also have a slower metabolic rate?
Well, no, I mean, it's slower metabolic rate per kilogram body weight or per centimeter squared, yes.
But overall?
But overall, absolute, no, of course, like an elephant is going to burn way more and require way more calories than a field mouse in absolute terms. See what I'm saying?
Yeah.
Okay. So how we can measure this is, so what is then a calorie? It's a measure of heat production. So to measure heat production, we can, one of the most cumbersome ways to do it, and I think we might have mentioned this in EXS 312, but we'll talk about it a little bit more in detail here. Because this number is of interest to us, it's important for energy balance, it's important for fueling activity, it's important for knowing the energy production of activities. We want to have accurate ways of measuring the caloric expenditure of an individual both at rest and during exercise. You understand? So there's a couple different ways that we can do that. The most cumbersome, expensive, and least available, but the most accurate, is with this. It's called a simple calorimeter or a room calorimeter. And quite literally what happens is that you have air coming in and out of the chamber that the person can obviously breathe in and out. And you have a jacket of water that is flowing into this side of the chamber and out of this side of the chamber. And this is typically in the form of a pretty small room, but it's big enough to put like a little cot in and maybe a little couch and a little desk and a piece of exercise equipment or something like that. So you put somebody in here, you seal them up in this what's called a room calorimeter, and then you literally measure the amount of heat that they give off by measuring the difference between the water coming in, which is at a known temperature, and the water leaving, which is going to be the water at a known temperature plus the heat that the person let off. Do you understand? Any questions on
Wait,
that?
the water does not touch them?
The water does not touch them. The jacket of water goes around the room, and then the heat that the person generates,
How quickly does it like flow through?
I don't know.
Also, if like whatever that jacket of water,
Sure.
doesn't it couldn't that absorb some of the heat coming off your body though, and then make the
It-
water like less warm than your actual body temperature? Does that make sense?
No.
Okay, so you're measuring like the heat production.
Yes.
Okay, but like whatever the water is in,
Yes.
can't that absorb some of the heat as well
I think
from your body? Is what I'm
potentially,
saying. Okay.
but they either have that calculation or they know how much it's gonna conduct, or the whole goal is to heat the material that the water is running over, and then the water picks up that heat. One of those two things. Good question. So the point is, with all of this, the overall point is that this is the most accurate way, but there's only like 10 of these in the country, right? And they're hard to function, they're hard to get working, they're hard to keep working, they take a lot of maintenance. There was one at Colorado State that was built, I think, a couple years after I arrived there as an undergrad. It literally, I went to school there, got 3 degrees from Colorado State. I lived in Fort Collins for 12 years, and they never got that room working and eventually tore it down. So there's issues with it. But if you need a really accurate, if you need to do a study that requires, especially of resting metabolic rate, this is your thing, right? So one of the things that, like, if you wanted to do a study to address the myth that multiple meals throughout the day keeps your metabolism going, and keeps you burning more calories, right, and keeps it more efficient, then this is the type of thing that you would use if you wanted to do that study.
As opposed to just 3 meals a day or something?
Or, yes.
I
Yes.
don't know if you support it or not.
What's your
entirely
take on that?
sarcastic.
I feel like he does not support it.
Yeah.
What's your take on that?
Well, the data would suggest that it doesn't exist. I mean, that there's no difference in your
No.
metabolic rate. Yeah.
Like, cause some people are like, oh yeah, like I eat like frequently throughout the day, like
Correct.
small portions throughout the day, blah, blah,
Yes.
blah, keep my metabolism going
Yes.
anyways. So it's
That's-
not like not a real thing.
Correct.
No.
That is not a real thing. Not only is it not a real thing, but you basically are just keeping the hormone insulin elevated throughout the entire day. And insulin is the most one of the most powerful suppressors of fat breakdown and stimulators of fat synthesis that, like, the body produces. So it's doesn't alter your resting metabolic rate, but it also encourages fat deposition and suppresses fat breakdown. Okay, so measurement of oxygen consumption. Okay, so that's direct calorimetry because you're directly measuring heat production under these circumstances, right? But the thing that we really want to get to, and the thing that's accessible to us, and the thing that all of you need to know, if not forward and backwards in at least one of those directions, in regards to being competent exercise physiology graduates, is this idea of indirect calorimetry. Right? So indirect calorimetry is the idea that there has to be physiologic things that are very closely correlated with the amount of calories that an individual consumes. Okay? So, and basically what happens is that when an individual is at rest or during exercise, they're consuming what from the air? Oxygen, and blowing off what based on the exchange of that? Carbon dioxide. All right, so we're consuming oxygen, we're blowing off carbon dioxide. If we can measure oxygen consumption and carbon dioxide production, then we can relate that very closely to the number of calories that we're burning. Okay, so the more oxygen that you're consuming, the more calories that you are producing. Because what oxygen consumption does, as we'll see next week, oxygen consumption, maybe at the end of this week, but oxygen consumption fuels aerobic metabolism. So we start talking about things like using the mitochondria and glycolysis and breaking down carbohydrates and breaking down fat and turning those things into what energy source for muscular contraction and chemical reactions? What's the common currency for energy in the cell? What do we burn down carbohydrates in order to produce what? ATP, right? You all have taken anatomy and physiology. I know it. You had to get in this class. So, and you've talked about this stuff before, right? So when you consume oxygen, then if you can measure oxygen consumption. Now, what's interesting is the first exercise physiology studies where they wanted to know what oxygen consumption, they rigged up these one-way valves that basically you put this mask on or over somebody, and then you have them run or walk on a treadmill or whatever, and they're breathing in fresh air, and you know what the oxygen consumption of fresh air is, right? Because we have that data, we know that, 20% atmospheric pressure, blah, 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 right? Then we just need what comes out after you've inhaled and processed that. We need what you blow off, and you can compare those things, right? So we know what's in the atmosphere, and then we know what you've blown off, and the difference there is the carbon dioxide that you've produced and the oxygen that you've consumed. You understand? So this guy named Douglas invented these airtight bags, and they used to catch them in bags. So you'd be running, and you'd have a little exercise physiology intern hooking up these bags to your one-way valve that allows air in to go down to your lungs and back out, and then there's a valve that opens only, it's directional. It's kind of like how blood moves through your heart, right? It's pressure related and directional. And so then they would literally collect these bags at different time points and then analyze the gas that was in those bags after the experiment to figure out how much oxygen a person was consuming. Now, I don't know, sometime after doing that, they were like, well, collecting all these bags of air is a pain in the ass. It'd be cool if there was like something better that we could do. So they created oxygen and CO2 analyzers based on voltage, like what different concentrations of oxygen and CO2 does the voltage meters, right? So then, and there's also, you can actually collect a portion of the oxygen and carbon dioxide and then measure it with oxygen and CO2 sensors directly. So there's two different kind of approaches. And this is called indirect calorimetry. Right? This is what the VO2 max test is. We're going to be doing this in lab. So we have a metabolic cart. It's called a metabolic cart because it's portable and small, and you don't have to have these bags, right? And a person runs on a treadmill and they breathe into a mask. Now ours is an open air system where it's only collecting a sample of every breath, and then based on the voltage readings, it does a whole bunch of calculations to calculate, right? When I was in grad school, we used a different type of metabolic cart that actually had one-way valves and collected all the gas that you blew off, put it into a mixing chamber, warmed it to an even temperature, and then measured the oxygen and carbon dioxide with CO2 and O2 sensors. Right? The point is that if you are consuming 2 liters of oxygen, that is the equivalent of about 10 kilocalories of work completed, all right? And the average person is somewhere in the neighborhood of 2 to 3.5 mils or liters per minute of oxygen consumed, okay? So you're burning about 10 calories per minute, but this depends on the type of substrate that you're consuming. It also depends on the size of the individual and a whole bunch of other things. So we're making a lot of generalizations, but the idea is that if we know what your total oxygen consumption is, and if we know what your weight is, then we can figure out how many milliliters of oxygen you're consuming per kilogram of body weight per minute. Okay, and we can extrapolate that out, for example, over a 24-hour period, and get a really good estimation of your resting metabolic rate. Or we can measure it while a person is exercising, for the entire time that they're exercising, and that gives us the most accurate, accessible, accessible measure of exactly what the caloric cost of that exercise effort was. Because we're calculating the amount of calories that were burned based off the amount of oxygen that was consumed, and we know per liter of oxygen how many calories a person burns.
Depending on the workout, depending on like the particular exercise.
Well, if you
Wouldn't
do,
it be different depending on?
correct, it would be different, but that's just it. Like if I put you on a treadmill and walk, that's going to have a different oxygen consumption because the oxygen demand is going to be different than if I put you on a treadmill and have you run, right?
So the higher oxygen
Consumption, the
that-
more calories you burn,
Okay.
and
But
the
if
harder you're
like-
working.
Okay, but if you're like people that are like in better shape and stuff,
Yeah.
they breathe slower, they have like a
Yes.
lower oxygen
Yes.
consumption, so they burn less calories.
Correct.
Than someone that's not in shape.
Yes, for a given amount of work. So this is an issue, right? Especially when this is why we'll talk moving forward about things like polarized training. It has nothing to do with muscle confusion. It has to do with stimulating the system in different ways so that you're not just in the same rut of efficient movement. Because like this is a big challenge when you're working with like morbidly obese people or other individuals that are trying to lose a certain amount of weight, and then they lose some weight and then they start to plateau, but they do the same 1 mile walking course every single day at the same time of day in the same way at the same intensity, right? That initially is something their body is really inefficient at, and it gets them a big kind of it costs a lot of calories. But once they get into a little bit of shape, and especially once they adapt to that specific activity, they become efficient. Now, here's the thing. If you're trying to lose weight, inefficiency is your friend, which is counterintuitive. Because the whole point of getting into shape is so that you can do more things and it's not as hard, or you can be more competitive and it's not as hard, right? You can play basketball for longer or at a higher intensity and sustain that intensity, for example. But if you're just trying to like be fit and lose weight or stay weight stable or these types of things, which a lot of people have that as a goal for their exercise program, but then a lot of people go and they run, 3 times a week, they run 2 miles and it's the exact same route every single time, right? But one of the things that we've seen generally is that when you're thinking about what exercises you're going to do during a week, you want to do a lot of different kinds. So bike, walk, run, sprint, jog, do circuits, go swimming, right? Did I say bike? Yeah. Right? So that's exercise mode. So you want to mix modes. Oh, resistance training, weightlifting, hucking the chains. You guys call it that? I think that's like the coolest name
Pumping
for
iron.
weightlifting, and no one says it.
Pumping iron.
What, hucking the chain?
Hucking the chains.
Never heard
That
that.
doesn't sound right.
Yeah, it doesn't sound.
Doesn't sound like
good.
weightlifting.
I don't know. Hucking the chains, baby.
No,
I love it.
It doesn't fit.
Just means like getting work in.
Mm.
So the point is, and if you talk to like really good strength and conditioning coaches, they'll say, what's the perfect like strength and conditioning program? And the good ones, be careful and wary of the ones that say, this is what it is, and write you something really specific. Be much more excited when you see someone that says, we're going to mix exercises and we're going to do a bunch of different things at a bunch of different speeds, at a bunch of different intensities, at a bunch of different weights. Like, that's how you get response, right? And when you mix those things properly, then you're always stimulating the system's getting a benefit, right? And then you stave off inefficiency, if you will. Or you keep inefficiency as a big part of what you do. Right? And this also occurs at the elite level. For EXS 451, we read this paper about European and Scandinavian Olympic level and national level athletes. And they got these athletes to either do all HIIT training, all long, slow endurance training, or a mixture of both that they called polarized training. That's why I use the term polarized training. And these are elite athletes, are already like don't have a lot to go up in, right? And the most benefit across the board was from the ones that mixed modes and intensities. They did high intensity work, they did resistance training, they did long, slow. And when I say long, slow, I mean long and slow. I mean like you need to go, like I went on an hour walk this morning with my dog. Like we just went on a nature walk up 12th Street. It was wonderful. But the point is like that's a workout for the day, right? Does that make sense? Even though the oxygen consumption was probably low, the calorie consumption, I don't have to eat a whole bunch to recover from that workout, but I was still stimulating the low end of my aerobic system, which I want to be efficient for reasons that we'll see later.
Okay, so it would be more efficient for you to do that than if you went on like 6 mile run.
Well, yeah, because I ran 16 miles on Saturday, and now I'm trying to like stimulate the system. I'm trying to stimulate the system in a different way because I have repeats tomorrow, and I don't like running on back-to-back days.
Okay.
See what I'm saying? So like tomorrow is a HIIT training, and I'm not saying that I'm that I'm great at programming. I'm just saying like you want to mix these things, right? Mix intensities, mix ways, and we can tell how many calories you're burning when you do these different things by the amount of oxygen that you consume. It's how we. It's how. Why don't you just bump it off the table, line it up, and snort it? Okay. So, for those of you listening, a student in the front row just like shotgun 2 scoops of pre-workout, and now he has white powder all over his chin. Okay, so
I'll be ready right after.
I know, I appreciate it.
Yeah.
Timing is critical. So with indirect calorimetry, and here's the thing. There are certain things that we don't know what the effort is required to do those things, and it's important to know those so that you can fuel properly. All right, so one of the things, for example, that is going on currently, we have 4 capstone students that are working with wildland firefighters to try and optimize their training and performance when they're out fighting fires. And for them, they describe to us, well, we'll work anything from this long to this long, and we're digging ditches, and we're cutting trees, and we're thinning, and we're hiking, and we're carrying packs. And then you just say like, well, I guess that's a lot of calories. And then you just eat a bunch, right? Nobody has a good understanding of how many calories and how much oxygen they're actually consuming. Not only that, but we have in excess of 300,000, even a very lean individual, like a lean marathon runner, has in excess of 300,000 calories stored in adipose tissue. Right? We're talking lean individuals, 5-6% body fat, they have enough calories to fuel like 35 consecutive marathons, right? If you were just walking. But and we'll talk about all this, right? But intensity plays a big role in what you end up utilizing as a fuel source. But we can tell how much oxygen and how much fat and how much carbohydrates a person is using for a given exercise if we know the oxygen consumption. Right, so this is really cool. So now there are lab-based masks that you can use to collect this data, and we have this in our lab, and we're going to do these. But there's also now field masks that take advantage of modern technology that allow us to do this. So, in fact, we just earlier this year. I was able to secure purchase of one of the first models of a validated field-based VO2 mask where that entire setup on the computer and everything is in a piece about this big. and it wraps around a mask, and then it talks to your smartphone. And in real time, while you're out hiking or running or at the gym or riding a bike, it gives you your oxygen consumption in real time, right? Not only that, but after that workout, it gives you oxygen consumption. It gives you your total amount of oxygen consumption, would give you your total amount of calories. So like you could wear this, for example, during a basketball practice and know exactly how many calories you burn during a basketball practice, which is really hard to do because it's not steady state exercise, right? There's these bursts and there's these recoveries and there's these different things like that. And so all of a sudden you're like, well, how much do I eat after that practice? I guess it was pretty hard. I guess I need quite a bit of calories, but you see what I'm saying? So these are technologies that are really, really useful and would and are important for you guys to know about, because they're now turning into field instruments that you could have access to if you were a head strength and conditioning coach, if you were a coach, if you're in a position and you had a little bit of a budget and you could do these things and you know how to use that information, not just collect it, but actually use it. Indirect calorimetry is actually one of the most applicable things that you'll learn in exercise physiology. Okay? So, if you have a 60 kilogram subject and they breathe 60 liters per minute total, inspired air is 20.93, you can figure out how many liters of total air that a person consumed over a period of time, say a minute, and then you multiply that by the percentage of oxygen in the air, and you can figure out, and then you get the delta between what they are inspiring from the air and what they're blowing off, right? So if they're inspiring 20.93% of the oxygen of a volume, and then they're expiring 6.93%, then we know that 4% of the total amount that they consumed or that they moved through their lungs is going to be what they consumed. Does that make sense?
Only 4%?
Yeah. And that is going to be higher. You're going to take a greater percentage of the oxygen in the air as what goes up. Yeah, the intensity of the exercise, right? So sitting here, you don't need all 20.93% of the oxygen that's in the air. You can get away with just, especially if you're efficient, then you can get away with consuming a lot less than that. You see what I'm saying? But you start exercising, now all of a sudden the expired O2 percentage starts to go to 16, then 15, then 14. You see what I'm saying? But there's a ceiling on what your lungs are capable of extracting and exchanging, and there's a ceiling to the amount of hemoglobin that you have in the system and the capacity of that hemoglobin to actually carry oxygen and be saturated. You understand? So it's always going to be some percentage. You never are at 100% efficiency in terms of pulling. I mean, that's why blood doping is such a big way to cheat for endurance athletics, because you increase your capacity to extract oxygen from the air.
That's not true.
What's not true?
I said that's not cheating.
Oh.
It's open. You're just putting something in your body you already have. So.
That's a different conversation. So so VO2 of that person, and that's the volume of oxygen, not the volume of air that they're consuming, right? So the amount of air that you're moving in and out may be 60 liters per minute, but the amount of oxygen that you're extracting out of that 60 liters per minute is 2.4 liters per minute, all right? And 1 liter of oxygen consumed is equivalent to 5 calories burned. Okay? So, and that's really important, because if I put if I put the mask on Emma and then she does a basketball practice with it, and we can we can measure the total amount of oxygen that she consumed during that hour and a half or 2 hours, then if we have that in liters, we just multiply it by 5, and that's the number of calories that she burned during that period of time. See what I'm saying? Super useful. And it's much more direct than trying to measure calories based on things like, even though it's indirect calorimetry, it's a much more accurate way of measuring calories than even heart rate or movement, estimating movement. Because it's literally measuring what your muscles are using from an oxygen standpoint for both the generation of power in the moment as well as recovery. And what we'll see is that there's a thing called post-exercise oxygen consumption, where like if you did a 30-second all-out sprint, you might not use a lot of aerobic, you might not use a lot of aerobic metabolism, but your, how do you explain this? Like, do we stop breathing heavy immediately when we stop doing work, when we're exercising hard? No, you keep breathing. So your oxygen consumption while you're recovering is greater than what is being demanded of your work at that moment, which is nothing. You're just standing there. Does that make sense? So you still take into account the oxygen debt that you incur when you do anaerobic exercises, when doing activities like soccer, basketball, lifting weights, those types of things. Because you have to consume that oxygen at some point to repay the debt you created to produce the anaerobic power. Is this making any sense at all? It'll make more sense in like 2 weeks when we talk about anaerobic and aerobic activity. Okay? So now, if you consume oxygen at a rate of 2.4 liters per minute, and you have 1,000 mils per minute that you're consuming, and you can normalize this. Hang on a second. Ooh. Just wait a second. So you can normalize the amount of oxygen that a person consumes by dividing it per kilogram of body weight. Okay? Now here's why this is important. Because a really large, out-of-shape individual is going to have a higher oxygen consumption than a really small marathon runner if they were to, say, get on a treadmill and run for a couple minutes at a given rate, right? And then you would say, well, how is this person in better shape than this person? And it's because they're a larger individual, they have more metabolic tissue, so their absolute oxygen consumption is going to be much higher. But if you divide their oxygen consumption by their body weight and normalize for it across weight, then you end up with mils per kilogram body weight per minute. And if you weigh less and divide that into a number, you're going to get a bigger number per kilogram body weight than if you weigh more and divide that larger number into it, right? So that's how you look at, when somebody says, well, what's your VO2 max? You're talking about mils per kg per minute. You're not talking about the total maximum amount that you're able to consume, because you can't compare people with that because people are different sizes. Okay? All right.
So essentially,
Thank you.
bringing in more